Greetings viewers, in this video we'll attempt Cambridge A-Level Further Mathematics, Component 3, which is Further Mechanics. This is Variant 3 from the May June 2025 series. We'll attempt question 2 now. The particle P of mass m is attached to one end of a light elastic string. So elastic string means we can approximate this string to become a spring. And it has natural length A. So let me just write it down, all this information. The natural length or unstretched length L0 is A. Modulus of elasticity lambda is mg. And the other end of the string is attached to a fixed point O on a rough plane. So rough plane means there is some friction. This plane is inclined at an angle of 30 degrees to the horizontal. P is held at rest at point O before it's being released. So there's no kinetic energy beforehand. And then it slides down with a frictional force of this magnitude. And we want to find the distance that P moves down the plane before coming to rest. So let's sketch out this entire situation first. So we have a plane that's inclined 30 degrees to the horizontal. So let's say this is the ground. And it's a rough plane. And first of all, initially, the string is here at point O origin, with the particle is also here. Maybe use red color to indicate the particle is there. So that particle P is still here. But then after it's being released, the origin O is still here. And then after it's being released, the particle maybe dropped somewhere here. So that the string, it also, because it's an extendable string, so it has some extension. So maybe we call this length or the stretch length as L. Then we also have the height that it falls. We call this delta H maybe. Okay, what else information do we have? Also, we have the frictional force FF is 11/30 mg. And we want to find the distance that it moves down. So we want to find what is L. Okay, so what is L? So the entire stretch length of the string lah, basically. Most appropriately, we have everything in terms of mass here, so we probably will use the conservation of energy method. It states in the closed system, the change of total energy in the system will always be zero. So the energy cannot be created or destroyed, only transformed. So initially, it's at rest. Kinetic energy initially, there's zero. Spring energy, there's also zero. Because it's not stretched, or it's not even, yeah, it's not stretched at all. And then maybe we'll set the datum at this point, at the lower point. So we set this as a datum so that the potential energy at this point is zero. So the change of the potential gravitational potential energy will determine by the change of height. We put here change of potential energy will be mg delta h. Delta h, let's try and see if we can solve it in terms of L. Yeah, because we want to find that L, so we will probably use in terms of L is better. So delta H is the opposite, right? This is 30 also. Opposite of this angle, and the hypotenuse is L. So it's using a sine. So it will be L sine 30. mg L sine 30. And sine 30 you should know by now is half. So I'll just rewrite it like that. Okay, so there is potential energy, and that's the initial point. So this is the initial point. After, at the final point, we want to find when it comes to rest. So also the kinetic energy final will be zero also, because we want to find it at rest. What else energy we have? We have the spring energy at this point, because it will have because it's elastic. So after it fall, it will stretch some amount, and we're gonna use this, or we're gonna find this by using the formula here. This one, elastic spring, E is the energy, right? So lambda x squared over 2 L naught. X squared in this case, x squared is just the extension. X is the extension, where we can write it as the stretch length minus the unstretched length. So x, there'll be the stretch length is L minus the unstretched length is A, original length. And we square it. Lambda is given us as mg. Then 2 L naught, the unstretched length, that's A. So that's the spring energy at the final point. What else? We need to consider the work done by friction here. So the work done by friction, that will be FF multiplied by the distance. or in this case it is acting along the same distance, right? So we don't really have to use dot product, but you should know, I think it's in syllabus, right, that the work done has to be along the same direction, so it's a dot product. But in this case it's already along the same direction, so we don't need to consider that. And mg in this case, sorry, ff is this 11/30 mg, and the distance is traveled, of course, there will be L. That's the work done against friction. Okay, so now we can use this one. The initial energy will be equals to the final energy. At the initial point, what energy we have? That is only the potential energy, right? Because the datum we set it on top, so the potential energy on top, that is half mg L. Work done against friction will always appear at output because there is work, or the initial energy is being used to overcome the work done by friction, or work done against friction. So we put the work done against friction on the right hand side of the equation at the final point, and we also have the spring energy at the final equation, or the final state. mg exists on each of these terms, so we can just cancel it, and now it's just a matter of solving for L. Okay, this is sort of a quadratic in terms of A and L, right? So I think it's best if we can do some factorization, because it's not a single, or like, yeah, it's not, you cannot use a quadratic equation here also. So we just try and factor it. And the two values of L, or two expression for L, you should be able to get this. Now, do we accept both? Is the answer is no, because L, we have to think again back to the question. L is the length, or what we have set. This is what I have set as the variable. L is the distance that it traveled from the start to the end, while A is just the unstretched length of the string. So it does not make sense that the string does not extend fully and or stretch even more compared to the original length. So definitely the distance that the particle travel will be larger than the length of the spring. So given that L must be greater than A, okay, A is the unstretched length again, and L is the stretched length. So we have to reject this one. So we only have one answer, which is 5/3A. I think that's what the question one, right? Find in terms of A the distance that P moved down. Yep. So that is the final answer. One answer only. Next, it's given that P remains at rest in this new position. Find in terms of M and G the magnitude of the frictional force in this position. So they want, or you have to deal with the forces here, so it will be always useful to sketch the free body diagram. So let's say this is the surface, this is the string, so there is tension there, there is a normal force there, always perpendicular, right? Perpendicular to the surface. Then the friction. So friction, I'm going to say it occurs this side. So that's the friction. Then we also have a gravitational force, mg. And yeah, for the coordinate system, you can resolve it however you want, but I'm going to do this one, y, x. So actually for friction, yeah, that's why I resolve it like this. Friction you only need in the horizontal direction, or the x direction that we have assigned here. And first, let's resolve this weight into the horizontal direction also. So the what trig ratio, it was the 30 was, where is it? Okay, at the bottom here. So 30 is at the bottom here, and it will be here also lah. Okay, 30. No. No, 30 will be here. Okay, because, okay, let's say this is 30, means this will be 60, and let me say the blue is 60, right? The blue is 60, and then this entire thing is a right angle, if you can recall. This thing is right angle, so 30 minus 60, or 90 minus 60, that will be 30. So that's why here is 30. And for the mg in the horizontal direction is opposite 30, so we use a sine. Okay, sine of 30. So in the x direction, our sum of forces, at this point it remains at rest. What it means is there is no acceleration. So the resultant force by the first law, Newton's first law, inertia, no acceleration, the resultant force is 0. So we have assigned to the left or the left diagonal that is a positive, so t is in the positive direction, ff is also positive, and mg sine theta is going to the right, so right diagonal, so it's negative. So ff we have mg sine 30 minus t. What they want again? In terms of mg, okay, so what is t? T using the formula again. This time is this one. T is lambda x over L. Lambda is what? Lambda is given to us in the question as mg, modulus of elasticity. X is just the extension. Extension, what it means is the stretch length L minus the original length A. Then the original length is at the bottom A. So here my notation a bit different. L naught is the original length, L is the stretch length. Yeah, so this will be the expression for tension. Because L we already found, right? Yeah, L we already found as 3 over 5A. Sorry, 5 over 3A. 5 over 3A. So this thing, we can replace it with that expression. So L we replace it with that expression, and this whole thing can simplify to 2 over 3 mg. So that is our expression for tension. In sine 30, we know that is half mg, and tension, we know that is 2 over 3 mg. So we get a negative 1 over 6 mg. Okay, so in this type of application where we get a negative doesn't mean it's wrong immediately, but it just means we assign the direction wrongly. As we recall, we assign that the positive x direction is towards the left. This is positive x. So meaning negative x is to the right diagonal. So what it just means is ff is towards the right diagonal. Doesn't mean it's wrong, but the magnitude of the frictional force, so we just take the positive lah, okay? It will be 1 over 6 mg, and this is in the units or dimension will be in Newton lah, okay? So yeah, doesn't mean it's wrong because it's negative, it just means you assign the wrong direction. So ff should actually be this way. Okay, so thanks for watching.